All right, let's go ahead and go. Thank you everyone for joining tonight. So I'm Chris Gunning. I'm the chapter chair for the IEEE Boise Computer Society chapter. And the co-hosts for the event tonight, in addition to the Boise chapter and Boise section, are the Computer Society chapters for the Lone Star section for San Diego, Dallas, Orange County, San Fernando Valley, Seattle, and Utah, as well as the San Fernando Valley YP Affinity Group. Again, thank you everyone for joining tonight. Just a couple logistics details. So during the talk, if you have a question, you can go ahead and raise your hand, and you do that using the reactions button in your Zoom window, or you can type your question in the chat window if you prefer. And then we'll have general Q&A at the end of Anthony's talk. During that time, Anthony will just call on folks who have raised their hand, and you can unmute and ask your question. So moving to introduction. So Anthony is a software engineer based in Chicago. And I first met Anthony in the fall of 2018. That's when he was a student at Boise High School. And as a senior, he was already working with one of the top cybersecurity professors at Boise State University. And we invited him to give his first IEEE talk to our Boise Computer Society chapter that spring. And then I was fortunate to have him work with me as an intern at HP the following summer. And after that, he attended Columbia University, and he interned at several companies, including 5Rings, Datadog, and Amazon, as well as doing research at Oxford and also at Columbia's Hefner Biomedical Imaging Lab. So Anthony initially developed DeveloperGPT in spring of 2023 for a graduate seminar at Columbia University. His background includes machine learning research at Columbia University and the University of Oxford, as well as software engineering firms roles, as I mentioned, at multiple technology firms. With that, I'll go ahead and turn it over to Anthony.
Hello. Can everyone hear me?
Yes.
Perfect. All right. So hi, I'm Anthony. I'm a software engineer based in Chicago, and this webinar is going to provide an introduction to building LLM-powered applications using DeveloperGPT, a project I made last year as a guiding example. So the goal of this talk is to explore the potential of modern LLMs for software applications. I'll cover three main sections. First, some background on LLMs, including key terminologies such as foundation versus instruction-tuned models, as well as the basics of prompting. Next, I'll give an overview and quick demo. And then finally, I'll discuss some core concepts and considerations of creating large language model powered applications from a developer's perspective using DeveloperGPT as a guiding example. So if you're wondering, is DeveloperGPT just another thin wrapper around LLMs? Yes, it 100% is. The goal here is to explore the extraordinary power and versatility of modern LLMs and how you can build powerful LLM-powered applications relatively easily. So LLM, or large language models, are deep learning models trained on massive amounts of text, which enable natural language understanding and generation. And they're so-called large because they have billions of parameters or more. So for example, GPT-3 has 175 billion parameters, and GPT-4 is rumored to have over 1 trillion parameters. And what makes these latest LLMs so powerful is they can be used for many applications that they weren't specifically trained on through prompting. So just some state-of-the-art models you might be familiar with, such as GPT from OpenAI, Gemini from Google, Llama from Meta, Mistral from Mistral AI, and Claude from Anthropic. And there are, of course, tons of LLMs out there with new ones coming out every day. If you look at, say, Hugging Face models, for example, you'll see thousands of LLMs. So a base LLM is known as a foundation LLM, which is trained through self-supervised learning on large amounts of text. And foundation LLMs are typically trained with the primary objective of language modeling, which is predicting the next word given the previous word as context, or something similar. And as a byproduct of this training, they pick up on knowledge and understanding about a broad range of topics and also learn emergent abilities. So some examples of emergent abilities include things such as in-context learning, instruction following, reasoning, computation, and the like. And they're so-called emergent because they're present in these large language models, but may not have been present in these smaller language models that preceded them. And so once these foundation models are trained, they can then be fine-tuned for a wide range of downstream tasks. So fine-tuning more generally is when machine learning models are additionally trained on domain-specific information or tasks. So some examples of famous foundation models include the GPT family from OpenAI, Bloom for Big Science, and BERT from Google. Instruction-tuned LLMs are foundation LLMs that have been further trained by supervised learning on labeled input-output pairs, specifically where the input is some natural language instruction and the output is a desired response from the model. And instruction tuning improves the ability of the large language model to follow natural language instructions and tasks in general. And this training is typically combined with some type of reinforcement learning to help better align model response with human intentions. So while foundation models are trained to predict next words of text sequences, that language modeling objective I talked about, instruction models are specifically trained to follow instructions. And this distinction affects how we prompt them and how we use them in the application. Instruction tuning can be considered a type of fine tuning, but there's a bit of a distinction between instruction tuning and fine tuning. So fine tuning is typically training a model to perform a specific task or specialize in one specific domain, but instruction tuning is fine-tuning a single model to follow natural language instructions in general. So prompting is representing different tasks and problems as natural language input to the LLM in a way that enables the response of the LLM to solve the problem effectively. And prompting is a rapidly evolving field. There's tons of different prompting techniques, and prompting can also depend quite a bit on the LLM that you use. So why do we need to prompt LLMs? Before the current era of these large language models, many machine learning models were trained using supervised learning on specific tasks with labeled inputs and outputs. As mentioned earlier, LLMs are trained on massive amounts of unlabeled text, and by virtue of their size and massive volume of training data, they gain an understanding of a broad range of topics that we can harness or activate through prompting. And shown here are just a couple common prompting components. These are taken from Google's Vertex AI reference and are by no means exhaustive or definitive. So things such as objective, persona, context, response format, reasoning steps, and few-shot examples. And I'll provide more examples of these components and how they're used later on in this presentation. Beyond those basics, there's also tons of other prompting techniques that I won't get into, like chain of thought, self-consistency, and the like. So none of these prompting techniques are strictly required. Many of the state-of-the-art LLMs are tuned to perform very well at tasks with minimal to no prompting, but good prompting can improve large language model performance, especially for more complex or specific tasks. Within prompting, there's this concept of zero-shot prompting and few-shot prompting. Zero-shot prompting is how many of us, myself included, might use ChatGPT or other language models on a day-to-day basis, typically by just asking the model to do something with no examples. And this generally works pretty well on most state-of-the-art instruction-tuned models and for basic tasks that the LLMs have already seen in their training data. Few-shot prompting, also referred to as in-context learning, is providing the model with a few examples for a given task you want it to perform, as well as a task description. And this can have a pretty big impact on LLM responsive quality, especially for complex and specific tasks. Especially if you decide to work with a foundation model, you typically will need to use few-shot prompting in order to get the LLM to complete the task in the desired manner, as the tasks may not be, to quote the author therefor, similar to the format of the pre-training data. Really, the idea of few-shot prompting is similar to the human idea of learning from analogy. So it provides a way to reinforce elements in the LLM's response mentioned explicitly in the prompt, such as the output format or reasoning steps, and can even allow strong LLMs to implicitly pick up on aspects of response you want to mimic. So in this example here, the few-shot examples reinforce the JSON formatting we explicitly want it to give, and explicitly mentioned in the prompt. And it also implicitly prompts the LLM of the desired JSON structure, such as that we want nouns and verbs with keys, as well as the fact that we want the output verbs in lemmatized form, which is their base form. It's important to note that few-shot prompting is not actually updating, training, or tuning the LLM in any way. The LLM is totally unchanged. It's just presenting the task to the LLM in a way that hopefully improves its performance. So with all that background out of the way, on to DeveloperGPT, which is an open source LLM-powered developer productivity tool I first made last year as a sort of a personal project. So it has two main features. The primary feature is natural language to terminal commands. So for example, you can ask it something like, find all Python files in documents modified in the past day, and it'll give you the command to run, or something more complicated than that. And a secondary feature is chatting in terminal with LLMs. This is pretty much what it sounds like. You can just talk to different LLMs directly in your terminal without having to go to a browser tab. And DeveloperGPT is by no means a unique product. One of many similar applications is GitHub's Copilot in the CLI, which was just made generally available this March. But unlike GitHub Copilot in the CLI, DeveloperGPT is completely free to use and fully open source. I'm obviously biased, but I think another advantage of DeveloperGPT is that it supports many different LLMs beyond just OpenAI models, as shown in this table here. So by default, DeveloperGPT uses Google Gemini 1.0 Pro because Google has a relatively generous free tier and up to 15 requests per minute. It also supports open LLMs such as Mistral, Gemma, and Zephyr, the GPT family for OpenAI, Claude 3, Haiku, and Sonnet from Anthropic, and even offline quantized Mistral LLMs that you can run on your own device locally using Llama CPP. And because this field is so rapidly evolving, support for different LLMs may be added or removed at any time as API access changes or new models are released. So for example, Google just released Gemini 1.5 Flash just last week, which probably DeveloperGPT will be using as its new default model once they get around to testing it. So here's a quick demo. Let me know if you can hear the audio of the demo. First off, you can download and install DeveloperGPT using pip install. The main feature of DeveloperGPT is natural language to terminal commands. For example, say I want to find all Python files less than 5 kilobytes in size in desktop/demo. I can just use DeveloperGPT command and type my request. DeveloperGPT will provide me with the command to run as well as an explanation of how the command works. I can also revise my request. Let's say I only want to include files that are modified in the past day. Now that I'm happy with the result, it can execute the command for me. I also have the option to copy the command to my clipboard. By default, DeveloperGPT uses Google Gemini 1.0 Pro because it's free up to 15 requests per minute thanks to Google. However, DeveloperGPT also supports other LLMs including OpenAI GPT models, Anthropic Claude 3, Haiku, and Sonnet, open LLMs hosted on Hugging Face including Gemma, Mistral, and Zephyr, and even LLMs you can run offline on your own device. You can switch between these different LLMs using the -- model flag. Natural language to terminal commands also supports a fast mode with -- fast, where commands are provided without any explanation. As a secondary feature, DeveloperGPT also provides in-terminal chat with all supported LLMs. This includes offline LLMs running locally on device with the -- offline flag. Shown here, I can chat with quantized Mistral running locally on my Mac on how to create a timing decorator in Python. All right, cool. So that's the demo. Let's see if I can go to the next slide. First off, all right. So for DeveloperGPT to be useful, it needs to work well, especially if you're going to use the commands that it provides. So to do some evaluation, I came up with 85 natural language command requests. These are things ranging from Git, file system, networking, libraries, and tools. And this isn't a rigorous evaluation by any means. These are top @1 results graded using a combination of manual testing and GPT-4 evaluation, but allows us to get a sense of the accuracy of DeveloperGPT when used with different LLMs, and it also allows us to compare against GitHub Copilot and the CLI. So by default, DeveloperGPT uses Gemini Pro, which is free to use and has an accuracy of 84%. Using DeveloperGPT with GPT 3.5 has the best accuracy at roughly 95%. And by comparison, GitHub Copilot and CLI only achieves 78% accuracy on this 85 natural language command evaluation set. And even when we're using a smaller 7 billion parameter open LLM, such as Gemma or Mistral, DeveloperGPT achieves a respectable 67% accuracy. So just to provide some context, here's an example of one of the requests in the 85 request evaluation set and some responses from various LLMs used in DeveloperGPT. The first command it provided is correct and works as intended. The second one is almost correct, but uses -- all, which displays remote tracking branches and tries to delete them, which results in an error. A third command is incorrect because it assumes our current branch is named master or main, which may not be correct. So as you can see, it's not necessarily a trivial problem to solve. And if you want to give DeveloperGPT a try yourself, you can install it by PyPy using pip install. You can also check out the source code on GitHub. When choosing an LLM to use with DeveloperGPT, the best accuracy is GPT 3.5. It does cost a bit of money in terms of OpenAI credits. Gemini 1.0 Pro is also free, and which is also used by default. And if you want to run something offline on your device, you can use Quantized Mistral that runs the LLM on your device. So now on to developing with LLMs using DeveloperGPT as a guiding example. Some basics of development with LLMs. So LLMs take tokens as input and output, not plain text. And you can think of tokenization as the process of converting between plain text to a common language representation, which is tokens, that LLMs understand. And this process depends on the LLM used, and different LLMs typically have different tokenizations. For many LLM APIs, the process of tokenization is typically abstracted away from you, and you can just provide the API with plain text in and get plain text out. But tokenization still matters because LLMs have a limited context window, which is the maximum number of tokens they can accept as input at once. So typically when you're developing an application with LLM, you still need to count the number of tokens in your input text using some tokenization libraries, such as tick token, and trim down the input if the token count exceeds the context window of the model used. Tokenization also affects the cost of using LLMs, with models like GPT 3.5 for OpenAI charging for 1 million tokens of input and output. So one really important concept when developing applications with LLMs is that they're stateless. So that means the conversation history or context awareness you see in LLM-powered applications, such as ChatGPT, is an illusion made possible through software. So what does that really mean? So the LLMs themselves don't retain any state or information between sessions. That is, LLMs generate responses based on only the content of the current input and any knowledge it's pre-trained on, and they don't have any knowledge of previous non-training inputs or outputs. So what this means is that if your application needs the LLM to be aware of some previous conversation or prior history, you need to store this past history in software and need to provide the LLM as input every time it needs it as context. I do want to note though, while LLMs themselves are technically stateless, inputs and outputs to online LLM APIs may still be used for training and may be retained by the provider, as in don't provide confidential or proprietary information to LLM APIs. So to kind of provide some grounding for this, shown on the left is a sample conversation between a user and a large language model in a ChatGPT-like interface. The LLM is aware of history and can respond to questions relevantly. And shown on the right is what the first and second input to the LLM might look like as implemented in software to allow the LLM to be conversation history aware. So shown in this example, in software, we store the input and output from the LLM from the previous conversation turn and provide it to the LLM as part of its second input. And this is a bit of a naive example, but this shows the mechanics behind it. So what makes developing with LLMs so powerful is that through prompting, we can turn LLMs into our very own fully customizable and highly adaptable API. So in our application, we can prompt the LLM to handle almost any sort of input and give us back exactly the format and data that our application wants. So in this example, part-of-speech tagging LLM application on the right, we want the model to respond with a specific JSON format with nouns and verbs as keys. So we provide the desired structure of the JSON in the prompt, along with a few few-shot examples, and the LLM will respond to a wide variety of inputs in that specified JSON form. And what makes this even more powerful is that we can even offload some logic or complexity that we previously had to put in code to the LLM to handle. So going back to the example on the right, we can use prompting and few-shot examples to get the LLM to classify an input as valid or invalid, and then return the appropriate JSON response, instead of us having to do validation logic in code. So all this to say, previously before LLMs, to do the same example application, we'd have to use some natural language library in Python in order to do lemmatization and part-of-speech tagging. But now with LLMs, we can offload all that to the LLM to do, and all our application needs to do is just parse the output JSON from the LLM. Essentially, with the power of LLMs and prompting, it's really easy to develop a shockingly powerful application that's just a relatively thin wrapper around an LLM. There are some downsides though. So one difficulty of writing LLM-powered applications is that you need to be able to handle possibly unpredictable or unbounded output, hallucinations, or even deviations from expected structured output. So prompting can help you constrain this, but generally you also need to write some code to defensively check for that. And to show how much complexity can be offloaded onto the LLMs, here's a breakdown of how the natural language terminal command feature works in DeveloperGPT. So on the left the user provides the natural language request to the terminal interface, which handles path completion, session history, LLM initialization, and mode selection. And depending on the LLM selected, one of the LLM adapters constructs a prompt using the context, instruction, user examples, and the user input. And here, contexts are things that we programmatically give to the LLM, such as user system platform and date and time. We also have multiple LLM adapters to interface with different LLMs. So prompts vary a bit between LLMs. The LLM adapter sends the constructed prompt to the LLM as an input and gets back from the LLM a JSON output, which contains error status, commands, and explanations. This is cleaned by the adapter. And I want to note here that we don't do any valid or invalid request validation in code. So if I were to provide a nonsense command, we don't do any of that validation in code. Rather, we offload this validation to the LLM to decide and to return to us in JSON format. The JSON is then passed to the terminal interface to be displayed in a nice format with syntax highlighting, along with the option to execute any commands provided. So as you can see here, DeveloperGPT is just really just a thin wrapper on LLMs. And this just shows how simple it is to create an effective LLM-powered application. There's not much code, the LLMs are doing a lot of the work. So shown here are some key components of the prompts that we use in DeveloperGPT for the natural language to terminal command feature. Specifically, these are the prompts used for instruction tune models, such as Gemini Pro, GPT 3.5, stuff like that. Mentioned earlier, you can see here that we provide the platform and date time programmatically to the LLM within the prompt as context. And this allows the LLM to provide commands tailored for the machine it's running on. The LLM is also prompted to decide whether a given request is valid or invalid, as shown on the bottom, and to return an appropriate JSON response. DeveloperGPT has two modes, fast mode and regular mode. In regular mode, we prompt the LLM to provide sequence commands and explanations in JSON format. But in fast mode, we just prompt the LLM for just the commands, only the commands in a JSON list. DeveloperGPT also prompts the LLM with a few shot examples. And crucially, it's important to note that these few shot examples contain an example of an invalid command request and a response. And this is to nudge the LLM to be able to recognize invalid requests instead of trying to provide nonsense commands for an invalid request. So if you recall the differences between instruction tune models and foundation models, which are that instruction tune models are fine-tuned for instruction following, while foundation models have a language modeling objective, so that it's like text completion or next word prediction. So in order to support the same natural language to terminal feature, DeveloperGPT uses a different prompt for foundation models. And specifically, the task is reframed as a text completion task. So we give a few examples and it ends in assistant blocks, such that the foundation model hopefully completes the text with the correct commands. And using the same instruction task prompt for foundation models wouldn't work because foundation models are not tuned to follow instructions. And this just shows how foundation models differ from instruction tuned models, especially in the way they're prompted and integrated to accomplish the same task. So with prompting being a key part of developing LLM applications, developing good prompts obviously requires a bit of evaluation and iteration. So I did a bit of evaluation myself on DeveloperGPT with different LLMs and prompts for the natural language to terminal commands feature. And this was done using the same 85 natural language command request set mentioned earlier. First, I wanted to examine the effect of prompting the model for command and argument explanations and command sequencing on accuracy. So if you recall, that's regular mode. And this is contrasted with fast mode, in which the model is just prompted for commands themselves. So we can see here that the additional prompting for commands and argument explanations results in improved accuracy for many of the LLMs supported by DeveloperGPT. So we see that for GPT 3.5 with DeveloperGPT, the accuracy increases from 79% to 95%. And for Cloud 3 Haiku, we see a similar accuracy improvement from 79% to 88%. We also see a pretty drastic effect on the smaller Mistral 7 billion instruct model, with accuracy increasing from 35% to 67% with additional prompting. So if you recall, Copilot and CLI had an accuracy of about 78%, which is roughly on par with DeveloperGPT with GPT 3.5 in fast mode. So it seems likely that the additional accuracy that we're gaining in DeveloperGPT over Copilot and CLI might be due to the additional command and argument explanation prompting. And this kind of shows the effectiveness of good prompting. So even in this relatively simple application, a better prompt can result into up to a 30% uplift in accuracy, depending on the LLM. You'll notice here that the two Google LLMs, so Gemini Pro and Gemini 7 billion, are quite interesting as regular mode, fast mode, the additional prompting doesn't seem to really affect their accuracy and even seems to hurt accuracy. So if you look closely, you'll see that Gemini's worst performance in regular mode is actually due to the increase in the number of invalid JSON responses. It's due to the more complex JSON output structure demanded in regular mode, which Gemini doesn't seem to be able to consistently produce. So in fact, if you look at the breakdown of purely incorrect commands, Gemini Pro with this additional prompting actually has slightly lower percentage of incorrect commands. The second way I wanted to evaluate prompting was to look at the effect of few-shot examples on command accuracy. So looking at these results, the larger models, so GPT 3.5, Gemini Pro, and Haiku, they don't seem to benefit much from few-shot examples, only a marginal improvement in accuracy, if any at all. On the other hand, the smaller 7 billion parameter Mistral 7 billion instruct seems to benefit much more from few-shot examples, with over a 20% improvement in accuracy. And most notably, the foundation 7 billion parameter Gemma model from Google is unable to output properly structured JSON without few-shot examples. And this is in line with existing literature, which shows that instruction 2 models generally require less few-shot examples and prompting to follow NLP tasks when compared to foundation models. And the idea here, once again, is that foundation models have this language modeling objective, so you need few-shot examples to help reframe the task as a text completion task. This also seems to suggest that the performance difference that we see between DeveloperGPT with GPT 3.5 or Claude over Copilot and the CLI might be due to the additional command and argument explanation prompting and not the addition of few-shot examples. The one thing I wanted to emphasize, so even though few-shot examples didn't improve LLM performance for these larger LLMs, so Gemini Pro, Claude 3 Haiku, and GPT 3.5, they're still valuable because they help nudge the model to be able to recognize invalid requests. So on a test set of 10 invalid requests, for all LLMs except for Claude 3 Haiku, the addition of few-shot examples helps the model to identify a greater number of these invalid command requests. So an example of an invalid request is something like mount my fridge to my Bluetooth network or something nonsensical. So even for Claude 3 Haiku, well, it seems like adding few-shot examples doesn't affect accuracy. Having few-shot examples in the prompt makes the model output more predictable and structured. So specifically, with few-shot examples in a prompt, Claude 3 Haiku consistently returns nicely structured JSON output. But when you don't provide few-shot examples, Haiku sometimes provides extraneous text around JSON output. And this has a detrimental effect on model usage and cost, especially because output tokens are typically charged at a higher rate than input tokens. And also this extraneous text adds complexity to your application as you need to clean it and extract it or whatnot. All this to say is that adding few-shot examples generally helps LLM performance in terms of accuracy or structured output. So I want to emphasize that all these prompting evaluation results are by no means rigorous. They're more of a demonstration for the specific use case. The key takeaway here is that developing applications with good prompts can improve LLM performance. And to develop good prompts, you need to do evaluation and iteration. And as we saw for DeveloperGPT, better prompting can improve accuracy by up to 30% and can even help constrain model structured output. Something to keep in mind is that prompting depends on the LLM used. So smaller LLMs might require more prompting or more few-shot examples than larger LLMs to achieve similar results. Using foundation LLMs might require different prompts because of that different language modeling objective versus instruction following objective. And ultimately, good prompts can't save a weak LLM. So if you try some of these prompts with an LLM from a few years ago, it just won't work very well. It just won't work very well. When it comes to using few-shot examples and prompts, including an example of an invalid request can help nudge LLMs to better recognize invalid inputs from your user application. Using well-curated few-shot examples is important. If you have errors in your few-shot examples, the LLMs will replicate these errors. And this may seem obvious, but when I first developed this over a year ago, I had a few typos in my JSON examples, and some LLMs would actually replicate those typos, and which gave me a lot of headache. Few-shot prompting also depends on the LLM used, as mentioned earlier. So if you use a foundation model, you might need to use more few-shot prompting. And some LLMs are better at following small details or implied elements in your few-shot prompts than others. More prompting and more few-shot examples is not necessarily better. So longer prompts generally result in slower inference speeds and higher LLM costs. And a concise, well-worded prompt with well-curated examples might perform better than a longer, lesser prompt. There's a lot of active research on prompting and different techniques being discovered out there. These are just the basics. But overall, developing good prompts for your application requires iteration and evaluation. If you want to read more, there are prompt engineering guides from OpenAI, Anthropic, Google, and others all over the web. I also want to quickly touch on structured output. So as mentioned earlier, a challenge of developing applications with LLMs is that you need to be able to integrate possibly unbounded or unpredictable output from LLMs with your application code. So if we can get the LLM to consistently give a structured output, it makes integration a little bit easier. So beyond using better prompts, there are many techniques or frameworks that you can use to get better structured output. The easiest is simply just to lower the model temperature, which makes model outputs more deterministic. Some APIs nowadays support like a JSON response format parameter, which guarantees the output of the model to be JSON. And you can also use something like a second stage to ask the LLM to self-correct itself to correct any deficiencies in its initial output. Besides these basic techniques, there's also dozens of frameworks for LLM structured output that you can use that are shown here. And all this to say, though, you don't have to use any of these advanced techniques or frameworks to get structured output. So DeveloperGPT was first created in the spring of 2023 before many of these frameworks were well developed. It just uses prompting with lower temperature settings, JSON response format when supported, and some output validation, and it works pretty well. Finally, there's many LLMs out there. So choosing an LLM to use for your application is dependent on many factors. So for simplicity, I'm going to focus on a few factors that I found relevant and less so on enterprise or production considerations. This isn't a complete set of factors to consider. You should always do your research, but hopefully this provides something to think about. So first off, LLM performance is important. There are many benchmarks that assess model performance out there, but ultimately it comes down to playing with different models for your application and seeing how they stack up. So in the case of DeveloperGPT, we actually see that the LLM benchmark performance doesn't necessarily correlate with our specific use case. So for example, Claude 3 Haiku and Claude 3 Haiku and Gemini 1.0 Pro have a higher benchmark performance than GPT 3.5. But as you saw earlier on our evaluation set, GPT 3.5 actually outperforms both. The specifications or type of your model also depends on your application. So LLMs have different size input and output context windows. So if you need to be able to input lots of text at once, you may need an LLM with a longer context window. It's also important to note that not all context windows are equal. So some LLMs are better able to use information from long context windows than others. LLMs also have different inference speeds, which is how fast they're able to process input tokens and output tokens. Certain LLM architectures are faster. So for example, mixture of experts versus dense. And this also depends on the parameter count of the model. So typically lower parameter count models are typically faster for the same architecture. And whether you use a foundation model or instruction tree model also depends on your use case. Cost, of course, is a consideration. For many LLM APIs, the cost depends on the number of tokens of input and output for a given model. And also typically more advanced LLMs typically have a higher input or output token cost. And if you have the necessary hardware yourself, you can also run certain open LLMs locally, in which case the cost may just be the cost of electricity. Related to all the above is choosing between a closed model, such as Claude 3 Haiku, Gemini, or GPT 3.5, versus an open model, such as Gemma, Zephyr, or Mistral. There's a bit of a rivalry between the two, and it's a bit of a complex comparison, so I'll just give my opinion. So closed LLMs in general, they have the best top-end performance. They have lots of venture capital funding behind them or corporate support. They typically have pretty good, reliable, and robust APIs and have good documentation support generally. With all that being said, they're pretty easy to get started with. On the downsides, though, they typically cost more than if you were to run your LLM locally. They're also less customizable and transparent, and you're beholden to the company that created them. Open LLMs, on the other hand, are almost infinitely flexible and customizable. They're generally cheaper to use or even free to use, and they also have some pretty good support. The downsides are that open LLM APIs might be more prone to change. Models release very quickly, things change really quickly, and there's generally a steeper learning curve to get started with. And also, when it comes to top-end performance, so looking at the best LLMs, as of now, the best LLMs are still closed LLMs, such as GPT-4. So for example, with DeveloperGPT, supporting open LLMs requires a bit more ongoing work and maintenance as models are added or removed as APIs change. In contrast, though, something like OpenAI API, since I first created it over a year ago, I've only had to update that once. So that's a bit of a trade-off. And to put some other trade-offs in context for DeveloperGPT, we just look at the best 3 performing closed models. So that's Claude 3 Haiku, GPT 3.5 and Gemini 1.0 Pro and how much they cost, we can conceivably try to optimize for the highest accuracy per dollar by reducing prompting while maintaining performance. And if we do that, we can see that GPT 3.5 achieves the highest overall accuracy to cost ratio, while Claude 3 Haiku achieves a close second and third for the specific natural language terminal command use case. Finally, I wanted to go over different levels of building LLM-powered applications and explain how DeveloperGPT fits in the bigger picture. These levels are not clearly delineated. It's just my view on it. So level 0 is just how most people talk to ChatGPT. Level 1 is prompting. This is all about presenting the natural language request to the LLM in a way that extracts the most utility from the LLM's pre-trained knowledge. And prompting is really all that DeveloperGPT is doing with the LLMs. And you can get pretty good results as shown here, just using basic handcrafted prompts. Beyond handcrafted prompts, there's tons of prompting frameworks and tools that you can use, such as MetaPrompt, DSpy, and the like. There's also much more to prompting than what I talked about today. There are prompt techniques such as chain of thought, least to most, generate knowledge prompting, many things out there. Level 2 is augmentation. This is where LLMs are augmented with additional knowledge, memory, planning, tools, or the like. And some examples of techniques here are things like retrieval augmented generation, graphs of thought, or LLM agents. It's important to note here that levels 0 through 2, the LLM isn't being fine-tuned or updated in any way. It's just using additional software or data to augment and compose the other LLMs to make them more powerful. And for prompting and augmentation, there's also lots of tools and frameworks out there to make your development really easy and nice, such as LangChain or Llama Index. Level 3 is fine-tuning. This is the first level at which the LLM itself is actually being updated, so the parameters, model weights are actually being changed. This typically involves further training an LLM with additional data to improve performance on a specific domain or application. And it's typically a more involved or complex process. It typically requires more resources, either monetary or hardware. And finally, level 4 is just training a new foundation model or modifying an existing foundation model. And this is out of reach for most of us unless you have a big GPU farm or have lots of expertise. The takeaway from today, hopefully, is that modern LLMs really unlock a whole new world of software possibilities, and you can create some genuinely useful and exciting applications with just prompting and a few other basics. So that's all I have for you all today. Thank you all for listening. I will now take questions. And I see there's questions in the chat, so I will look at them now. Okay, I see most. Let's see here.
Yeah, I'm not sure there were any specific questions in the chat. So as folks have questions, if they just want to go ahead and hit the reactions button and raise their hand. And let's see, make sure, yep, so I just raised my hand and lower it as well. So yeah, so if you do have questions, go ahead and raise your hand. I see Daniel has one. So let's see, Daniel, I'm not sure if you can unmute yourself. Otherwise, Anthony, you should be able to unmute Daniel.
Anthony, can you hear me now?
Yes, I can hear you, yes.
Great, excellent presentation, great overview at high speed of the LLM status today. I have a question for you on your opinion for people who are interested in applications, in other words, to make the LLMs do useful things. When do you think an application such that it can take a body of PDFs, academic textbooks, academic articles, and be able to intelligently or with some awareness search in those, for example, to find inconsistencies between articles? In other words, an article might state that such and such is the best of theory and meets the evidence most compared to some other article that might claim it's a different theory that works best. When do you think such a thing might be available?
Yeah, I mean, so I'm not an expert on this field, to be totally fair, to be totally honest with you. I think there are techniques out there that can enable maybe part of what you suggested. So you can use something like a vector store, using something like retrieval augmented generation. So you can turn all these texts into embeddings and then do some type of semantic search and retrieval over them. So in that sense, you could conceivably build something like this that could, in theory, go through each article and then do semantic search for relevant bits from your vector store. and then compare for consistency. So that could be done today. If you're talking about giving the LLM all the documents all at once, I think that's probably a few years out. I think the longest context window LLMs today are 1.5 million tokens, I believe, or 2 million, I'm not sure, from Google, which can fit a lot of text, but probably not the volume that you're asking for. So I think to truly accomplish what you want to do with no additional software tools, I guess, or vector stores or semantic search, I think would need to wait till an LLM has, maybe 10 million, 50 million, maybe even unlimited context window. Yeah, hopefully that answers your question.
It is, except I'm not sure that just a semantic search would be sufficient. I mean, I'm looking for understanding as opposed to just sort of being able to diagram the English. Am I missing something, or maybe I misunderstand semantic search?
So I guess, can you rephrase the last question? Sorry.
Sure. I'm not sure I understand fully semantic search as opposed to understanding the general concepts of an article inside an article, such that it understands the concepts well enough not just to parrot them, but to actually contrast other concepts in other articles.
Yeah, I mean, to be honest, I'm not totally sure the answer to your question. I think conceivably with the idea of a semantic search is you're not just retrieving the text. So for example, like just off the top of my head, one way you could possibly implement this is you have some semantic, you turn all these texts into embeddings, right? And then you go for, say, article A, and you do a semantic retrieval for all articles that are similar to article A. And then you could feed all those similar articles to the LLM as a prompt. And then you could ask the LLM to look for inconsistencies. And then from there, it's really just up to how good the LLM is, whether it's able to interpret and understand versus just, as you said, parrot. I guess that requires evaluation. We'll have to see. Yeah.
Thank you very much, Anthony. Excellent questions or answers.
Thank you. I see a question from Valerie. Did you use sensitivity, recall, specificity, or other measures? Sorry, I'll read that slower. Did you use sensitivity, recall, specificity, or other measurements besides accuracy? The answer is no, I just used accuracy. I figured it's either correct or not correct, especially because as a developer, I'm just going to type my natural language request in, and I'm just going to probably blindly follow, to be totally honest, what it gives me. So I just care if it's correct or not. Hopefully that answers your question. Let me know if you want more clarification. Yeah.
So I've got a question. You'd mentioned on one of the slides, one of the knobs to turn was to lower the temperature, and I'm not sure what's meant by that. Could you explain?
Yes. So temperature is like a setting in models that reshapes the probability distribution of tokens as they're being sampled. So a lower temperature means that the model's only going to take the more probable tokens, while a higher temperature sort of flattens the distribution, that more tokens are possible, if that makes sense. Okay. The token probability is more balanced. Yeah, hopefully that makes sense. So then lower temperature means more deterministic because you're just taking the most likely token. Higher temperature means you have a bit of more randomness involved. Does that sort of make sense?
Yeah, yes, it does. That makes sense. Thank you. So do we have additional questions from the audience? You can go ahead and raise your hand if you do. All right, seeing none, we can go ahead and wrap it up. Anthony, thank you so much for your talk today. I'm already getting emails from some of the folks who are on the call today, just to compliment you on your excellent talk and saying how interesting and useful it was to them. So that's very encouraging. That's awesome. And it was a wonderful talk today. So wanted to thank you so much for coming and giving this presentation today. I know you put a lot of work in to put it together. So I really appreciate that everything that you've done, and I'm seeing more comments in the chat window as well with thank you. So again, thank you so much.
Thank you for inviting me. Yeah, well, it's fun to talk about.
All right. And for folks that called in, so Anthony, go ahead and send your slides to me, and I'll go ahead and send those out to the folks who registered, and then you and I can also review the video and see if that's something that you want to make available as well.
Perfect. Sounds good.
All right. Well, thank you, everyone. Thanks to everybody who called in, and enjoy the rest of your evening.